Our next speaker is Peterson. I have too many affiliations, so correct me. So Dr. Peterson is an adjunct professor at Victoria University, Melbourne, and an adjunct senior fellow at the University of Queensland, St. Lucia, Brisbane, Australia. He's also a resident research fellow at the University of Leeds. He's going to talk to us about transition engineering to the water electricity nexus operating in building services and urban heat islands. Concept design is air conditioning really necessary. So the floor is yours.
And there's a tip on where to push the button. I thank you for letting me get some peer reviews and feedback from you. So please, if you don't have time for any questions, catch me later. Tell me where you think I'm wrong here. But I'm trying to get my ideas help to back up further research. I'm on the technical committee 4.2 for climate data, so I've been able to find out how to get a hold of the data sources that are used in the handbook, the fundamentals handbook, and I've been independently analyzing. Anyone in the world can actually download it from a NOAA web server. You get that? No, just this is the go button. Who's the next one?
It can be on the keyboard actually.
Probably safer for the just go next. Okay, so Ashbury talks you got to give people learning objectives. So I want you to learn a bit about bioclimatic design. I want you to learn about my little crazy theory of the -3 to +3 scale of what mode of HVAC system you need, where 0 is that passive works in using more energy going either way towards heating and cooling, dehumidification, humidification. I want to address the problem of daily data sets. If you use Energy Plus and IES virtual environment, you have to use hourly data sets, and they're very expensive, very hard to produce. There's a lot more daily data sets from all around the world. That's what I'm trying to introduce here. And I want to talk about urban heat islands. So bioclimatic design, they call them the magic blue arrows. The architects put magic blue arrows on drawings. The wind will just blow through here and passively cool everything. Will be just perfect. Unfortunately, the air doesn't always read the architect's concept design drawing, and it doesn't always work this way. There are limits to what this passive low energy stuff do, but there's a lot about this that reduces the need for energy intensive heating and cooling. Now, you might notice that the sun is moving the funny way around because this is from the Australian government website. This is public domain, so I was able to put this in the proceedings. I made sure that I only took things that they hired an artist to put that on, and there's a lot of things where they have a credit, a lot of examples about bioclimatic design. I think you know what I'm talking about. Now, the University of California seems to have got a lot of funding over the decades from the California Electricity Commission and the US DOE produce a lot of really powerful tools. Now this is from the University of California, UCLA architecture professor Murray Milne, and he keeps getting funding to keep producing this thing. It loads in energy plus weather files, puts your 8,860 data points onto a psychometric chart, and it shows what modes are going to give you relief from discomfort on an hourly basis, and it'll help you choose and sort of like write a brief, a design brief to a team of architects and engineers what you need for a given location. And that's really neat, but there's that problem of there aren't energy plus weather files for everywhere in the world. And so this is what I'm going to talk about is how do we pick up this beautiful chart? I found it really fascinating. How you can look at where is your comfort zone, and this is where you're adapting. You know, winter and summer, we have different expectations how we dress. But as you go into these points here, you can do passive low energy design, you can push the limits here, but then you're going to need heating systems coming this way. You come this way, there's limits to how far you can go with ventilation, either sort of natural convection or forced convection. There's not really a lot of differences as long as you design it to work. Evaporative cooling, unfortunately, has limits about where the wet bulb lines come. And direct evaporative cooling it is. I'm really keen on it where it works, and that's something I've tried to conclude in my paper where it would work. But a lot of places there are times when swamp coolers just don't do it. In Arizona, the monsoon comes, you're going to need some DX on point. These are these points up here. So another University of California tool that's really useful is the Berkeley tool, which is the Ashtray 55 adaptive thermal comfort tool. And you can fiddle around with all this stuff with mean radiant temperatures, and you can find out whether you can just borderline make some set of conditions pass or not. The point is, though, that as you're getting towards 30 degrees C, you're going to have to increase airflow, reduce stress, all sorts of things to be able to tweak it. But you're getting up over 27, you're really it's tricky, touch and go. You got to let people adapt. Now, the third thing I want to introduce here is the wet bulb globe temperature in the shade. And this is actually, I didn't have room in the paper to talk about this, but I'm quite passionate about this. I think the wet bulb globe temperature in the shade, that's without actual radiant sources, assuming a really well-shaded thing. Think of a tree, a really nice shade tree, and whether you're comfortable or uncomfortable, whether you're stressed in those conditions. To me, a really good passive architectural design ought to try to approach the tree. The shade tree is about the best you could hope for, with taking away all internal loads of different things and having really effective ventilation. That's the best you can do. But the occupational hygiene people have worked out where this wet bulb globe temperature is, how that relates to how much work you do, what sort of dress you do, and then come up with this thing that's sort of this yellow flag. And there's a paper in Nature that came out last year about where deadly heat and humidity combinations come through. And I found, I tried to write to Nature, they're looking at it, but they wouldn't quite publish my idea. I said the wet bulb yellow flag pretty much is spot on the same curve as what these guys did. This big analysis of fatalities all around the world. So I'm quite keen on the wet bulb globe temperature. Now, we have a joint school at Leeds University, and I'm now sort of becoming more employed in Leeds. I hope to win a fellowship and keep going at Leeds. We have a joint school in the Panda City in China, Chengdu, and it's a growing mega city. And if you take the Energy Plus weatherfall for there and take those 8,870 points and shade them, here's the sort of classic comfort area here. And then here I put these wet bulb globe temperatures. We only got just a handful of hours in that file that are yellow flag conditions. It's really not that stressful. It's a little bit uncomfortable. Then you get down to the black flag. Oh, sorry, that was, I've got my colors on. Then there's this white flag, I forget the color of this one, green flag, yellow flag, red flag, and black flag is really, really seriously deadly exposure. You don't get that, at least in that one. There could be an odd occasional heat wave, but in that typical year that's used for design things, there was only a couple of hours that showed up there. But those lines are sort of going, not at wet bulb lines, are sort of 0.3 of between weighted by wet bulb and dry bulb, assuming shade conditions. And then we've got our classic wet bulb lines, and this is 24 degrees wet bulb, that's quite high. And that's the absolute limit of what I've been able to read, where you would expect that a ventilation system would provide comfort. And you'd also, I've been saying in my paper, chop it off at 27 here. Down here, where evaporative cooling would work in that Chinese location, it's not many hours when direct evaporative cooling would be sufficient. Anyway, it's not in the paper, so forget about wet bulb globe temperature. Here's what I've got in my paper. I've got that 24 line, I call that the very humid temperature. You got your sort of normal humid temperature, 19.4. And from my literature, it seems like most books that talk about evaporative cooling say direct evaporative cooling stops at that level. Now, if you could just put a swamp cooler in, you'd be good in these areas. But without a swamp cooler in a lot of places, if you're not getting those conditions, by just having good ventilation, you can push comfort this way without actually using water and swamp cooler. So broadly, just really being crude here, I've got these three modes of going into the hot and three modes going into the cold and zero in the middle. So the winter modes are it's very rare, but in a few cases it seems like you need to just simply humidify. You don't need to add heat, you just need some really dry conditions. So that it's possible that there could be this first mode in winter. Then there's, actually heating the air. and there's, I call it the air source heat pumping zone, and then there's the icing heating. There's the sort of conditions where air source heat pumps can freeze up. Now, there are some really advanced manufacturers that have really good defrost cycles, but there's some real rubbish out there on the market that doesn't perform well at all. And there I'm saying, well, why not think about ground source technology or whatever, or just combustion to wood stove or solar or something. But I'm just trying to say there's a graduation of how much effort and work there is in staying warm in winter. And similarly, in summer, the first step is going to ventilation. The next step, in some cases, is direct evaporative cooling. And the third step is DX, direct expansion vapor compression cooling. So it's in my paper. I've given these, greater than or equal things. And maybe some people with swamp coolers, if you don't want to do ventilation, you use different criteria. But I've stated what I've done. And yeah, in that Chinese location and in most of the world, except I say in what do I say? Except in I concluded that the part summarized here. It wasn't many. It was UAE, Hong Kong, Kuwait, Qatar. You need, you're just not going to be able to do that at all. But in here. I had it in the paper. It was my conclusions. I've lost it, folks. But it was in my conclusions. Basically, Afghanistan, Algeria, possibly. A few places where swamp coolers will work. Okay, but it's quite rare. And somebody like this is just going to go. Now we've got to have aircon. I mean, look at the hours out here. You've got those. You've got yellow flag, green flag. Even this white flag is telling me that means you need it. And then with my definition, you get this sort of cut-off conditions here where you'd say, okay, I got to have this or that. But because I've got so many hours here, you're going to put it in. You're going to have DX, in which case you might as well say, well, you're just going to have a system that's going to run. And, you might be able to do something with a second system, a hybrid system. But you're going to make the decision based on having sufficient demand there. You're going to put it in. Now, similarly, on the other side, the icing condition. Now, in this case, they've got icing conditions here quite a bit, where they're going to have this freezing problem. They might actually decide they want to put a ground source system in to avoid that icing, in which case they'll have very efficient cooling and heating systems. But in other places where we don't have the icing conditions, you could have a reverse cycle air source system that's going to serve heating very well. And then even if there's not a lot of demand for here, even if you could do it with ventilation and direct evaporative cooling in some cases, I'm saying that'll throw you across the line into that. So like icing, here's a photograph I took last winter in Germany, just driving over a hill, and it was those sort of magic conditions, right near the freezing point. The difference between the dew point, or actually what we call frost point, same thing with saturation, within 5 degrees Kelvin there between the dry bulb and the dew point, and just even above freezing, stuff can frost, but it really will just choke up and load up coils so they don't perform very well. So that's my criteria there. So this is a little bit of a trick here. You talk about when this icing condition happens. It's when the difference is 5 degrees depression of dry bulb minus dew point. Okay, so that's all in the paper. And in the paper, I had a different Chinese city, which is in Sichuan province. But now, hopefully going to do work with the Shengdao case study. I've got more slides about Shengdao, but a very similar kind of pattern. You've got icing conditions in these places, which is going to say you're going to be interested in ground source technology if you want to go for a low carbon technology. You've got a lot of air conditioning, so you might as well have reverse cycle, but ground source in this case. This is sort of a tool to help you make that judgment. Now, looking at the climate consultant from UCLA, you get this hourly data, you can just toggle it and switch it so you can show the daily minimum and maxima. And what you find is that in a given day, there's typically a certain kind of amount of water vapor in there. So during that day, it tends to just track along from about sunrise until about 3 o'clock in the afternoon or so. There might be a weather event, and it might reset the moisture to a different point. So it tends to be where it's traveling this way. So my hypothesis is that daily data you can interpret because you can assume on any given day we don't need to have all these hourly observations. We just know how much water vapor is in there, and then we can model that all through. So in the case where we've got our campus at Chengdu, now we have students exchanging between both campuses. This is an example. Now, I just picked up in August. August is the hottest month. There's more change in moisture in August than in any other month. I guess there's like a buildup of afternoon thunderstorms during the day. There's evaporation going on. But still, it's only a fractional variation through the time of day. So I'm just trying to support my argument that this daily data set is useful. I just wanted to give you a taste of converting this stuff around. It's highly nonlinear. The Handbook of Fundamental Psychometrics chapter shows you it's a lot of nonlinear stuff. You got to iterate around. You got to have an algorithm to calculate what's going on between wet bulbs and dew points and so forth. And finally, here's Chengdu, our developing population. So this was 1984. There's this urban center, 2.5 million people. There's the airport. There's the weather station. And then 1991, the city's grown, 3.5 million. There's the weather station. And then 98, it's too bad this doesn't show up that well. The airport's still sort of out of the built-up area. You got 5 million people there. And then in 2005, we have 7 million people, and it's just starting to get out. The development's moving out there. The weather station's sitting there monitoring. We've got records, right? And then Landsat, unfortunately, they had to get a new lens because you can see it's things tracking it. So that's not really development. That's just Landsat. But there's finally the last one I've got. You got 12 million people there, and look at the urban sprawl as get out to our stationary weather station. That's the only weather station you have in one of the world's megacities, right? But I plotted my stuff out like kind of with a timeline. So I flipped over heating degree days upside down, cooling degree days. You can see definitely, and I see this in so many places. And I've looked at 10,000 of these, maybe not individually, but automatically. The cooling degree days are increasing. The heating degree days, look how much the heating degree days are dropping recently. The urban heat island's really kicking in there. The modes of HVAC systems, actually the icing conditions seem to have dropped off recently. The heating days when you'd expect heating has dropped off. The area of passives actually increased a bit. Ventilation, but DX air conditioning as a desirable mode is definitely increasing. Wet bulb globe temperatures in the shade, and I'm suggesting perhaps that's I think this white flag wet bulb maybe is a more objective measure when we really need air conditioning. You can see that's increasing pretty much like DX. I've taken, now with 10,000 sets of data, I've decided to just distill it down into median representatives of each country. And in my paper, I didn't have room for, I didn't think it was appropriate to tabulate big countries like China, the Russian Federation, the United States, Canada, Australia. It's too diverse. So I've only put small countries where you can say it's like kind of representative of like a province almost, at a provincial scale. But you can see that DX is a very large number of days per year in the global south. They're just needing aircon like all the time. We have a lot of time in high latitudes, even in the Middle East, when we don't actually need aircon. And here's where passive comfort days increase substantially. And you need to remind me if I'm running out of time. But in conclude, here's my conclusion. Okay, only Afghanistan, Iraq, Jordan, Kyrgyzstan, Namibia, Zambia, and Zimbabwe would be places where direct evaporative cooling would work. And if you let the criteria move by 1 day per year, then I would say that Argentina, actually, you got Argentina, here, where did you go? Argentina, 9 days there. And Algeria and Argentina, I would say. But what you find is that if you consider, this icing conditions, these ones which have a very small number of days when the icing is going on, you only need heating, then I would recommend that you would be looking at a heat pump. You probably wouldn't consider air conditioning anyway in summer, because a lot of these places are water challenged anyway. So direct evaporative cooling isn't going to be the only solution. You're going to need to consider both the winter condition in your summer design decision. So that's my sort of logic that I use to generate those. And I've only been able to tabulate, a limited number of results here. And it's quite dangerous because I'm trying to say something about a city, about a country, and it's not really any real representation of the country. It's just saying that the median representative of each of those countries is such and such. So shoot me down in flames if you don't like what I've said.
So we're a few minutes ahead of schedule actually, so we can take or entertain a few questions.
Eric, I don't have a question, I have a comment. I've got a home in northern Arizona where I've got an air source heat pump and I've seen it run down to -6F. But my honest opinion on defrost on air source heat pumps is it's worse between 35F and 25F. Because there's more moisture in there. On the site chart, you're in a larger, a wider spot of the site chart. And then as you get colder, as you get down to 20, 15, 10, there's actually less times it goes into defrost simply because there's less amount of moisture in the air. Just FYI.
But, yeah, so is this not published? This is the thing. I'm trying to capture that from you. I need to...
It's my observation that you're having a home there for 11 years. So.
Yeah. I think as designers, we need to capture these kind of rules of thumb. Right. Because the bioclimatic guys, they're architects. They're designing like the passive design. I think we have to put the HVAC practicalities on top of that to give this concept design tool in a way. Because the developer needs to brief the design team. They say, okay, I need aircon, or I need this or that. And, I want ground source, or I want air source, or, trying to get that ahead. So what I was able to read from the handbooks, suggested this other metric that I've applied.
Quick question. I don't know if you had data, when you looked at data from Lebanon.
I'm sorry, that you got missed out in this. I'll
That's
look
all
at
right.
it tonight.
It would have been interesting because it's a tiny country.
Yeah.
You have a lot of microclimates, two big mountain ranges and a valley. So it would be interesting to see differences across even this tiny place.
Well, there was some other small countries that I didn't dare put on there, like Switzerland is just crazy.
Right.
And there's no way I can say, this is what you do in Switzerland. Not doing that. And I really, honestly, I was thinking about that because Lebanon's not in there. I've got, hundreds of countries in there, and somehow Lebanon went, no, I can't comment on Lebanon. So Ireland's in there. Ireland is foggy, and I'd say that the air source heat pumps are terrible in Ireland, and you should put ground source in Ireland. I can see that from what I'm doing. I'm quite comfortable to come out and say that. But what do you think about Lebanon?
No, I mean, I'll be curious because, like I said, we have a lot of microclimates. You're here now, it's, 28, 29, and quite humid, it's at 70%. Drive up 20 minutes up the hills, and you have a different microclimate. Drive up even more, completely different. And go over the mountains, you have a bit more semi-arid environment. You're talking about very small distance. I would have been...
So there's one weather station in Eritrea, and that one weather station would suggest that passive design techniques would work in Eritrea. But is that really true for the whole country of Eritrea? Ethiopia, there's a lot more stations, and there's huge variability, but it still looks to me like you ought to think about passive design in Ethiopia and Eritrea. And I would say Morocco looks like a good one. I think Argentina looks like there's going to be places in Argentina where you should really think about designing without using so much energy. Maybe a bit more ventilation, use glass and controlling solar gain into buildings. But the thing I discovered is in this journey was that direct evaporative cooling is not going to work the way I hoped. I really thought, I'm going to show you a map of the world, and it's just, what I've come around to thinking is indirect. I really think we need to put water onto condensing units and boost the COP by putting the water onto that microclimate where those split system condensers were groaning away, and quench those and improve the EDR. But I think we're going to have to use refrigerative cycles the way I see it. I think the way I look at it, the world's all about vapor compression processes and just doing it smaller and more efficient.
Just be careful of putting water directly on air-cooled condensers from my other hobby, and the amount of solids that you have in the water themselves, dissolved solids, because they'll scale up a condenser and they'll go after aluminum.
What about RO? You're talking about RO.
RO I could buy, but then people say put deionized. Deionized is worse than anything because it's looking for ions. Mm-hmm. So I would buy RO. But again, you bought yourself a maintenance nightmare. And being in a hot city, we see people trying to make air-cooled equipment more efficient all the time. And what you have to be careful of is you lower the electric bill, but then you end up with a huge repair bill to fix the unit. That's the issue.
So the answer is it depends.
It very much depends. Assam's, his presentation talked about the service and the maintenance. That's the key.
So, anyone have a simple silver bullet? We're all looking for that one. I've been trying to find that for a long time, and I haven't come up with it yet. So, thank you.
Sure.
Great. Well, thanks everyone. Join me.
Thank you very much.